We also looked at the memory virtualization.
Come again?
We looked at the memory virtualization.
Okay, compute virtualization has 3 segments. And you're saying
yes.
under it, we looked at memory virtualization. Thank you. What else?
CPU.
Network.
CPU. Virtualization. And then?
Input, output.
Input, output.
Input, output.
Virtualization.
Virtualization.
Yeah.
Okay, so we said when we are referring to KVM, what do we introduce to help us manage our input and output virtualization?
We introduced KEMO.
We introduced KEMO, right? We introduced KEMO, but also we said to a certain extent, KEMO
yes.
is somehow.
Yeah, quick.
And if you want to improve on its input and output performance, we introduce something called VAT-IO, isn't it?
The LibVat. Yeah.
Okay, so that is compute virtualization. Someone also told us that we looked at network virtualization, and we came to understand there are some invisible kind of network devices inside the server. How do you call it? It was a virtual. It was a virtual switch. And we said if you have a virtual switch and it is spanning across different servers, we have what we are calling a distributed virtual switch. Okay. And we looked at, and also today we want to look at storage virtualization. And this is important because we have already looked at the compute virtualization, and we have already seen, because now we need our CPU to process the instructions and execute them, the memory to temporarily store those instructions that are being executed. And of course, we need input and output devices, which are going to fetch those instructions from where they are stored through the different bus drivers, from our storage to the CPU, from the CPU to the memory, and vice versa. We also looked at the network for us to be able to connect the different virtual machines and also with other different physical devices. We looked at the network architecture in a virtualized environment. But also now, there's something important here which we're looking at, which are calling storage virtualization. We need to now understand, where do these virtual machines in a virtualized environment store their files? How do they store them? And how is this kind of storage different from the typical or traditional storage architecture? And this is what we are trying to look at in this chapter. Okay, and we are saying that data has become an enterprise. Let me highlight data has become an enterprise's most important asset. Do we all believe this?
Yes.
And we very well know
Sure.
that for companies like Google, they actually don't sell so much of different products, but most of their money is coming from information related products, isn't it?
Yes.
Exactly.
And only the companies that have control over data or information are the companies which have the upper hand. So therefore, data has become an enterprise's most important asset to date. So how is data stored in the cloud? How is this different from the way it is stored from the traditional IT? This chapter, we will answer these 3 questions. So upon completion of this course, upon completion of this particular topic, we'll be able to understand Huawei's Fusion Virtualization solution. What did we say? What is Huawei's Fusion Virtualization product? Yeah, I've already said it's a virtualization solution, sorry. Okay, so understand the storage architecture used for virtualized environments, and also understand different types of disks, understand the differences between centralized and distributed virtualized storage, distributed storage, understand the differences between virtualized and non-virtualized storage, virtualized and non-virtualized storage, and also understand the different types of virtual machine disks, and understand the storage features of Huawei's virtualization product. Okay, so let us look at the first bit, the storage architecture for virtualization. Just a simple question before even we dive into anything. Where do the storage resources used by virtual machines come from? You have laptops, isn't it? How do you store data on your laptops? Are there any devices you use to store data on those devices?
Hard disk.
Hard disk. Okay. And how do you store data, let's say, on your mobile phones?
Internal memory.
Internal memory. Right. So in the same case here, we are saying that these virtual machines here, they get their memories from different underlying storage devices. They can get them from SSDs, from RAIDs, disks that are bundled together, from distributed storage, from centralized storage, from HDDs, and of course from disks as well. So these are some of the storage devices where virtual machines could actually get or store or get their storage resources. So how do virtual machines access the underlying resources? Because we have already seen that, yes, there are underlying resources. In your laptop where you create your virtual machines, there are underlying resources. So let us first look briefly at this storage architecture in a virtualize for virtualization. And don't feel so like there's a much, I'm throwing so many things at you. Worry not. Worry not, we shall be able to dive into everything here slowly by slowly. So we are seeing here at, let's look at what we are calling the virtualized. Let's look at what we are calling the virtualized storage. And in the case of virtualized storage, we have some two prominent kinds of storage. We are having what we are calling NAS, and we are having what we are calling SAN. Okay, and we're going to explain all this. But before even we look at them, we are seeing that there are some kind of underlying storage resources. There are hard disks here, which are either RAIDed together or put together. And after putting them together, we form our storage pool here. And after forming our storage pool, regardless of whether we are using NAS or SAN, we come up, if we are using SAN, we are going to come up with a logical division. We are going to get the storage pool plus our logical division to come up with loans or logical volumes plus our file system. Then we shall come up with our shared catalog. And in the case if you're using NAS, the network attached storage, we have already a file system attached to it, and we shall automatically have our shared catalog here, which now the virtual machines will be accessing and using as their storage devices. And we are seeing here different types. We are seeing raw, VMDK, VHD, and other types of resources. Just excuse me just a moment. We're seeing other resources. And let's also look at the non-virtualized environment here. When we are looking here at the non-virtualized environment, we are seeing that still we have our hard disk as underlying resources. From there, we can either choose to add a logical division on them, or have logical divisions in a distributed pool of resources after creating them. And then we have our still logical volumes, the logical unit numbers, and then the non-virtualized storage. Our virtual machines access our virtualized storage in that kind of arrangement. So our storage architecture for virtualization can also be either virtualized storage or non-virtualized storage. Okay. So don't worry about some terms which are here. They may be a bit confusing, but we are going to be able to explain them in detail. So here, as you have seen, like I've been explaining and I've been talking about, at the underlying structure, we have our hard disks here, which hard disks now, when you RAID them, and we're going to look at RAID in the next few slides and also try to understand what is RAID. When you RAID and put them together, they are going to form a physical volume. The physical volumes, now after having your physical volumes and after you formatting them, you are going to get your logical division. And after getting your logical division, we have our logical volume, which logical volume now after formatting is going to add a file system. And in this case, we're using NFS as our example, NFS file system here. And then this file system now, you're going to attach to the cluster. And after attaching to the cluster, we have a virtual file system for our virtual machines to use. And that also forms a shared catalog with a different supported files for that virtual machine. Let us also try to look at the non-virtualized conversion path for the non-virtualized storage. RAID or replication, you can replicate or RAID depending on what you want. After replicating or RAIDing, then you'll be able to come up with your physical volume. Let me clear this drawing from the screen. Then after you having the physical volume, you format it. Then you have, after formatting it, you have your logical volume, and then boom, you have your storage for your virtualized environment. So we're saying in this architecture, there are physical disks that are located at the bottom layer, and cloud disks are located at the top layer. Just like this diagram here. Let me go back to this diagram. We have our physical disk located at the bottom layer here, this layer here, and we're having our cloud disks located at the top layer. These are the bottom layers for our physical drives. And we are saying a series of operations such as logical partitioning and file system formatting are performed between two layers. And you need to be able to understand some of these operations. And also you need to understand the differences between virtualized and non-virtualized storage. Okay. Now, let me ask a simple question. Who of you have ever formatted a disk? Anyone? You have been here and you have ever formatted a disk? A flash, like a flash disk or anything that you have ever formatted?
Personally, I am.
You formatted a disk. Okay.
Yes.
Me too.
This is okay. This is Victor speaking.
Yes.
Victor.
Yes.
Okay.
Yes,
Right.
I'm getting you.
And I see also Kasule's hand was up. Okay, Victor, as you're formatting your flash or disk or any storage device, what do you think you are trying to achieve?
I'm trying to clear whatever data is there to allow me to put into new data.
To allow you to put into new data. Okay.
Yes. Yeah.
Anyone else?
Yes.
Yes.
I think for me, I clear it to create for me new sectors. In case it got some problem to create for me new sectors for storage.
Okay. I hear you.
Yes.
Yes, go ahead and talk to me.
Yes. For me, I think we format the flash disks in order to read what data is there, and also set like the required file system.
To set the required file system. Yes. So most importantly, what I wanted, thank you so much for saying that though your volume. Yes, most of the times we are erasing off data, but most importantly, as we are formatting, we are also actually setting the file system for our device. For example, let me say I wanted to, are you able to see my screen?
Yes, please.
Yes.
What screen are you seeing?
Yes, you can see it.
The one I'm presenting.
Yeah, this
Yeah, the
PC.
one with your partitions.
My partition. Let's say I wanted to format this guy here.
File Explorer.
And I right click
Server
on
D
it
and
and I come to format. Can I make this bigger? I don't know if I can make this bigger.
We can see it.
You can see it.
Yeah.
Yes.
Importantly, as you're formatting, there's an important section where actually you're able to allocate the file system. You give that drive the file system. And it depends on the operating system. Some operating systems support different given file system and some other operating systems do not. And this is one of the most important thing about formatting. Actually, in actual sense, you are formatting it into, or you are putting it into a format that is understandable and readable by that operating system. For example, you have already seen here that Windows supports a format called NTSF. Which other formats are supported by NTSF?
exFAT.
Yes, there is exFAT.
And
FAT.
There's FAT. FAT32, yes. And how about Linux? Could you be knowing file format supported by Linux?
UFS.
Yes, thank you. Any other?
X234, extension 234.
And is there anyone who knows the extensions for or the file system supported by Mac OS? I have a student who is using Mac OS, at least like about 2 or 3 of them. Also, Mac supports FAT, Mac supports exFAT, it supports Apple file system, APFS, and so on and so forth. Okay, so ideally when we are formatting disks, we are formatting them into a format that is understandable by the operating system, but in the process also all the data, all the partitions, all the segments on that drive are erased. So, but before we go ahead to look at formatting and all that, let's also try to understand about some physical hard disks here, physical types and related techniques. Okay. And I believe we are going to go through this chap because we have seen this and we have heard them and we have played with them, at least for most of us. For those who have not, don't worry, we shall go slow. So we are looking at one of the hard disks. And you realize today hard disk, yes, please. Let me try to mute you all. I'm trying to get some feedback. Okay. Are you all seeing this hard disk before even I start talking about it?
Yes.
yes, we can see it.
Yes, we are seeing it.
Okay.
Yes.
Have you all ever come across it?
Yeah, we have come across it.
You have come across it. Okay, we won't go so much
Yes.
into the underlying technologies that are in it, but here we are seeing this is a SATA disk, and we are calling it a serial advanced technology attachment, also called serial ATA, is a computer bus interface that connects host bus adapters to match storage devices. Using serial communications, the serial ATA bus uses embedded clock signals to check transmission clock, not only data, and automatically corrects the detected errors, ensuring reliable data transmission for SATA disks. The SATA interface is simple and the disks are hot swappable. One of the advantages of this kind of disk is that they are hot swappable. The material has other more content about it, you can go ahead and read more about the spindles, about the platters inside, but they are not really relevant as far as this course is concerned, because you're not computer engineers, but we just want to give you a brief idea of the underlying storage resources inside a virtualized environment. Okay, so here you are looking at the serial ATA or the SATA disk. Currently, SATA and SAS hard drives are commonly used and distinguished by the interface type. By interface type, I am meaning this kind of interface. Sometimes they also use the size, the inches, but mostly it is the interface type of the hard disk. So you need to know the advanced technology attachment interface first, and the ATA interface are integrated drive electronics ID interfaces. ID interfaces was those first drives which had pins on top. Maybe you could go and Google about them to know what IDE interfaces are, but still they're not commonly used today. Today we are mostly commonly using SATA hard disks, and because of that, interfaces. So what SATA does, it uses independent data interfaces and signal interfaces to transfer data. Before, they used to use what they are calling parallel ATA, which was a 16-bit data bus drive for data transfer, and it needs to transfer many additional support and control signals. And this was a limitation in the way it was manufactured, and also the noise it makes, and its signal voltage was above, I think, 5 voltages. So that's why SATA is now preferred, because SATA uses an embedded clock signal and a stronger error correction capability. Thus, there is reliability of data. When you're reading and writing to this drive, you know at least there's some kind of reliability of data. So that is SATA for you. So let us also try and look at SAS. We are saying here that serial attached, this word is a new generation. Sometimes they call it SAS. So like the popular serial ATA, it also uses serial communication to achieve higher transmission speed compared with the older parallel Hcia, or what we are calling SAS. And SAS improves the efficiency, availability, and scalability of storage systems and offers optional compatibility with SATA. And SAS had an interface that looks close or something like that. That is what we are calling SAS. There's also another type which is called nearline SAS, or nearline hard disk. So the nearline hard disk, or the NL SAS, they are disks a combination of a SAS interface with SATA disks. The rationale speed of nearline SAS disks is only 7,200 RPM. So performance is lower than that of SAS disks. However, with SAS interface, addressing and speed are improved. So addressing and speed are improved when we are using a SAS interface. So let us look at also some of the popular hard disk, or the kind of hard disk which is becoming very popular today. And I want you to take note of these things. We will have HDD and we have SSD. Okay, and we are saying a solid state drive. All these things that I've been showing you here prior are HDDs. These guys, SATA is an HDD, and we're looking now at SDD. And we are saying that solid state drive is a solid state device that uses integrated circuit assemblies as non-volatile memory. An SSD consists of a control unit and a storage unit. The control unit is sometimes called flash, or the storage unit is sometimes called the DRAM chip. An SSD is the same as common hard disks in terms of interface, specification, and definition, functionality, uses, and product shape and size. But although SSDs deliver fast, take note, they deliver fast read and write performances. They are low light because they have a chip inside. They don't have disks and platters and spin and wheels and motors. They don't have all those things. And low power consumption simply because they don't have all those other functionalities. And of course, they have compact sizes. They can be very small, which traditional HDDs cannot rival. So SSDs have shorter lifespan and higher price. Take note that SSDs have shorter lifespan and a higher price. They have a higher price because of their fast read and write performance, because the SSD is very fast as compared. You could actually go all the way to 6 gigabytes, copying 6 gigabytes per second, at least as per my SSD in my laptop, 6 gigabits per second. And this is the beauty of SSDs. And also they are shock resistant. Since they don't have a disk spinning inside them, they're shock resistant. Even if this guy falls, as long as the interface or the chip inside is not cracked or broken, most of the times you just pick it, grab it, put it back, and you're happy and you're good to go. That is an SSD. So let us try to compare them in terms of performance and the price. We are seeing here that this is our HDD. Okay, this is our HDD, this is our SSD, and we are seeing it has a better performance as compared to our HDD. And of course, our HDD has a lower price compared to our SSD. So we also have our SAS and we also have our nearline. But the price is too high for this and it's not commonly very used. And commonly today we are using these two, and I want to focus on these two in this class today. So maybe let me ask a simple question. If you wanted to have high performance in terms of read and writes, what kind of disk would you buy today?
Buy an SSD.
SSD.
You would buy an SSD. If you wanted to keep data for a very long time, like let's say it's a data center and you have some data you want to archive, which you don't want to frequently read from the hard disks, what kind of hard disk would you buy today?
HDD.
HDD. Why? Because the solid state drives, one, are for somehow very expensive, and two, they have a short lifespan as compared to HDDs. So thank you. You guys are in class. All right, so let us try to look at what we are calling centralized and centralized and distributed storage. So let us look at centralized storage. You already see the picture before even I start explaining anything. There's some central guy here with either replication or RAID disks here, and there are some other CNAs, or sometimes you call them physical hosts, connecting to this guy here. Forgive my drawings. We have different machines or servers pulling storage resources from one guy. And we are saying with centralized storage, it means that all storage resources are centrally deployed, like you see this guy here, and they are provisioned over a unified interface. So with centralized storage, all physical disks are centrally deployed in disk enclosures, and they are used to provide storage services externally through the controller. Sometimes we can use SAN, and sometimes we can use other technologies or NAS, and you're going to be able to see them later on. So we are saying that all physical disks are centrally deployed in disk enclosures, and they are used to provide storage services externally through the controller. Centralized storage typically refers to disk arrays. We have some kind of disks put together in one central location. We have binded them together, and our other machines are able to access and use those storage resources which we have centralized, which we have put in one place here. So based on the technical architecture, centralized storage can be categorized as SAN and NAS. SAN can be further categorized depending on how you're going to connect to it. You can either connect to it using a fiber channel SAN, or you can connect to it using an IP SAN, or even fiber channel over Ethernet. So currently SAN and NAS can be, we are saying currently SAN, fiber channel SAN and IP SAN technologies are what we are using today in a virtualized architecture, but also fiber channel over Ethernet SAN still has a long way to go to reach its maturity. So by disk array, we are meaning combining multiple disks into a logical unit. We are going to have here disk 1, disk 2, disk 3, disk 4, and so on, and we're going to combine it into one single disk unit, and you're going to see this animation showing you how we can have our RAID or replication there, and we RAID them, and then we combine them into one single logical unit where the different servers can read and write data from them. Okay, so each disk array consists of a controller enclosure. These are the controller enclosures. You can read about them. There are so many. HP offers you some. SAN, NAS are some of the common ones, and multiple disk enclosures. So the architecture delivers an intelligent storage space featuring high availability, high performance, and large capacity. So if we are looking at what we are calling NAS storage. Maybe let me go back to this slide. Sorry, we'll go back to this slide here with sorry to take you back with yes, with SAN, so that we can see some SAN very well as we're explaining it. This is what you're calling SAN storage. We are saying in centralized we can either have SAN or NAS, and now we are looking at the SAN storage. So SAN is what we are calling storage area network, and with which we are calling SAN. So with blocks as basic data access units, it is a dedicated high-speed storage network that is independent of the service network system. Keynote, it is independent of the network service system. So this type of network is implemented in the form of fiber channel storage area network, which are calling fiber channel SAN, or IP storage area network, which are calling SAN, and serial attached storage area network, which are calling SAS-SAN. So different implementation transfer data commands between servers and storage devices using different communication protocols and connections. Okay, so we are saying here that an emerging storage solution, SAN, accelerates data transfer. It delivers great flexibility, reduces storage complexity, alleviating the impact of transfer bottlenecks on the system and improving the efficiency of remote disaster recovery. You should also take note that SAN is a network architecture that consists of storage devices and system components, including servers and the need to use storage resources, host bus adapters that connect storage devices, and fiber channel switches. So while using SAN, all communications related to data storage, they are implemented on an independent network that is isolated from the application network. So if you're using SAN, you isolate this kind of network from our application network, which means that transfer data on SAN does not affect the data network of the existing application system, which makes SAN deliver higher input and output capabilities of the entire network without necessarily reducing the data network efficiency of the original application system. We can also choose to have redundant links to the storage system and also support high availability in the cluster, which will also improve on the reliability of data. So even if you are to use fiber channel CHAN, 2 network interface adapters are configured. Can I mute someone? Andrew, allow me to mute you because you have some borders in the background. Are configured on the network storage server, and one is a common network interface adapter. So if you are going to use fiber channel CHAN, we are saying we need 2 network interface adapters that are configured on the storage server. One is our network interface card. And this network interface card connects a service IP network, and the server interacts with the client through the NIC. And the other is what we are calling the HBA. Okay, is what we are calling the HBA that connects the fiber channel CHAN, and the server communicates with the storage devices through this adapter. Okay, so we have our fiber channel in the middle, we have our switch, and other applications are connecting to it. So IP SAN, take note, we are still looking at SAN storages, and we are saying that IP SAN has become a popular storage technology in the recent years. And I believe you all now know the reason why it is popular. Do we?
Mr. Ssendi.
You're already hearing the word IP. Yes, please.
Me, I'm currently lost.
Where are you lost?
It's like you've been giving a lot of information. It was very hard to keep up.
It was very hard to keep up. But you know what you're looking at right now?
Yes, we are talking basically about SAN.
SAN, which falls under centralized storage.
Yeah.
We are looking at centralized and distributed storage. Most of those things I've mentioned, some of them even don't need to cram. We need to just understand where you're coming from. And we are looking at SAN storage. When you're looking at SAN, we said we can either have NAS and we can have SAN. And we said the centralized storage, we have one centralized resource pool where we RAID or replicate our disks and bundle them into a logical, isn't it? Into a logical unit. And then different servers can access this centralized storage. Do you remember that part?
Yes, I remember that part.
You remember that part, yes. So now, we are looking at this now, the centralized part. And we are saying we have one, which is the storage area network. And also we are looking at the NAS, which we are going to look at later. And under here, that NAS, the SAN, we said it has 3 kinds of interfaces we can use. We said we can connect to it using one, which is fiber channel. And you know what fiber means? It transfers at the speed of light. So there is high speed transfer. We can use fiber channel SAN. We can also use IP SAN. And we can also use fiber channel over Ethernet. You remember? Though we said this is not yet very popular, but these are already in use today because they are in their maturity stages of development. We looked at fiber channel SAN and we said it has 2 types of interfaces if you want to connect to them. Okay, we said one interface is a NIC and another interface is a high speed bus adapter, the HBA adapter. But all these I'm just mentioning, you won't even see them appearing anywhere. I'm just saying, not that you cram, but you won't even see them. And you're advised to go ahead and read more about them. Okay? But this is SAN, which we are looking at. We are looking at SAN storage. And maybe to get you from where you're lost, we are saying SAN storage is a centralized kind of storage which can either be connected through fiber channel or IP SAN or even fiber channel over Ethernet. And we are saying that IP SAN has become also a popular network technology used in recent years. Isn't that where we were?
Yeah.
And we said the early, I was going to say now that the early SANs, most of them were fiber channel, meaning that data was transferred over fiber. We all know that also fiber is expensive, isn't it? That is already one disadvantage for fiber channel. It is expensive. We agree?
Yeah.
Yes, it's expensive.
And they used to access them as block-based access units. So due to incompatibility between fiber channel protocol and the IP protocol, customers who want to implement fiber channel have to purchase its devices and components. Its high price and complicated configuration, a large number of small and large number, sorry, someone was calling me. Okay, so fiber channel SAN is mainly used for mid and high-end storage that requires high performance, redundancy, and availability. So to popularize SANs and leverage the advantages of the SAN architecture, technicians consider to combine SANs with prevailing and affordable IP networks. You have an IP network on your computer, you have a network interface card, don't you? You don't need a sophisticated kind of equipment to connect to an IP-based network, isn't it? All you need is an Ethernet cable, isn't it? But you cannot directly connect to an optic fiber. You have to terminate it based on the cores it has, isn't it? And you also know it's delicate. So this means that IP1, they are affordable. So the IP SAN that uses the existing IP architecture is introduced, and the IP SAN is a combination of the standard TCP IP protocol. You guys discussed for me TCP IP last time. I did not even mention anything about this. You guys discussed it. Okay. And it also implements a block level data storage based on the IP network. So what we should take note is that IP leverages on the affordable or already the existing IP infrastructure, and it is based on the TCP IP protocols, which are common today and majorly or mostly used in our network architectures. So basically, what I was trying to say, my dear friend, between IP SAN and fiber channel is that IP SAN and fiber channel lies in the transfer protocol and medium. That is their difference. So what do you think is the medium for transferring data over an IP SAN? Could someone tell me what they think? Then also, Andrew, you can go ahead and ask your question. What are some of the mediums used in an IP-based network? Before Andrew asks, Ethernet cables, isn't it?
I think the internet.
Yes, Ethernet cables, Cat5e, Cat6e. Okay, so what do you think are the mediums we are using in a fiber channel SAN?
Fiber optic.
They're using the fiber optic cables. Awesome. Yes, Andrew, you wanted to ask something. Andrew, you can go ahead and ask. Andrew, your hand is up. Okay, so as Andrew is getting ready to ask, let me proceed. Okay. Come again. Yes, Andrew. Okay, so I think Andrew is having some failure. And we are saying when it comes to IP SAN, all common IP SAN protocols include common, some of the protocols that they use. Take note of this. ISC. I don't know how to pronounce that abbreviation, but ISC, SI.
ISCAS.
Yes, that one always gives me hard times. So we have also fiber channel IP. That is another protocol. And also we have iFiber channel protocol. Okay, so but pay maximum attention to this, because it is the fast growing protocol standard, and in most cases IP-SAN refers to IP or the network or the SAN storage that uses that protocol. Okay, just take note of that. Yes, please.
What is ISCI?
Is this Andrew?
No, this is Walter.
This is Walter. Andrew, I see your hand is up. Is everything okay? And I've just seen your message. I don't want to continue when you are having an issue. Andrew. Okay, Andrew, I think you can just drop me a message. Oh, yeah, you're trying to sort out your mic. Okay, all right, noted. So someone asked what is ISCSI in full. It is the Internet Small Computer System Interface.
Thank you.
All right, so let us proceed. I should be perusing through some of these slides because, and I actually, you go ahead and read more about them from the internet and from different slides. So IP-SAN has some of the following advantages over fiber channel SAN. So access standards or standard access. We already know that IP-SAN requires only common Ethernet cards and switches for connection between storage devices and servers instead of dedicated HBAs or fiber channel switches. That we already know. So in terms of access, we go with our IP-SAN. So long transfer distance, IP-SANs are available wherever IP networks exist. Currently, IP networks are the most widely used networks in the world. Kindly take note of that. Long transfer distances. So we are saying here that currently IP networks are the most widely used networks in the world, and good maintainability. Most network maintenance personnel have good knowledge of IP networks. Therefore, IP-SANs are more acceptable than fiber channel SANs. IP-SAN can be maintained using the developed IP network maintenance tools. Let me ask, is there anyone in this forum who knows how to terminate an Ethernet cable? Is there anyone who knows how to in this forum? You can maybe just put up your hand. Okay.
Yes.
Yosam is also saying they know how to. That is awesome. Is there also anyone in this forum who knows how to terminate a fiber optic cable?
Yes.
Who? Emmanuel?
Yes, Emmanuel.
Emmanuel. Okay. Is there anyone else apart from Emmanuel? Okay. All right. So you can see already that we only have one person who knows how to terminate a fiber optic cable here. And Nelson, we can't hear you, unfortunately. I think your mic is messed up. So that's why it is easy for us to be able to implement the IP-SAN as compared to the fiber channel SAN. So the bandwidth can also be easily expanded. Just a moment. Hi, Romeo. Hi, Romeo. Yes, please. Okay, could I please call you back? I've been in a class. I'm going to call you back after the class. All right, thank you. Sorry about that. So we're saying that bandwidth also can be easily expanded. With rapid development of 10 gigabit Ethernet, it is inevitable that the bandwidth of a single port on the Ethernet-based IP SAN can be expanded to 10 gigabits. Okay, 10 gigabits. We can also expand it. Remember, we also talked about where we can actually get these two links of 10 gigabits and we do our LCP. Remember what we meant by this? What does this do? Does someone remember? Emmanuel, you wanted to say something, please?
Yeah, it's the link aggregation control protocol.
Yes.
It can bundle different ports links and merge them into a link with a bigger, wider bandwidth.
Okay.
For transmission.
Thank you so much. Thank you so much. So all these advantages reduce our total cost of ownership. To build our storage system, that includes to buy the different disk arrays and access devices, personal training, route maintenance, capacity expansion, disaster recovery capacity expansion. With the application of IP networks, IPSAN helps customers significantly cut down the purchase cost of access devices, maintenance cost, and capacity and network expansion costs. If you need to expand a fiber optic cable, Emmanuel can tell you the process you have to go through. It is not as easy as you would expand your Ethernet network. So let us look at the next slide. That is SAN for you. Okay. Still before we move away from this slide, let us also look at the NAS, our network attached storage. One thing you should note with the difference already between SAN and NAS is NAS already is a file-based storage architecture or system. It is a file system-based architecture. This one, it is not file-based. So here we are saying it is a technology that integrates distributed and independent data into large-scale and centralized data for access by different hosts and application servers. You should note that NAS is a file-level computer data storage connected to a computer network, providing data access to heterogeneous group of clients. A NAS server contains storage devices such as disk arrays, CD drives, tape drives, or portable storage media. A NAS server delivers an embedded operating system to share files across platforms. So when you share, actually, when you access this, it will be more like you're accessing already logical unit numbers available to you in terms of folders and files, that kind of hierarchical architecture. So the inception of NAS is closely related to the development of network. After the inception of ARPANET, modern network technologies developed rapidly and the users have increasingly demand for sharing data over the network. So that's why those engineers or the storage engineers decided to one day try to resolve this issue, and we can use actually a dedicated computer to store a large number of shared files, because all of them storing the different files on their computers, and I need to access a computer from Emmanuel's computer, and Emmanuel needs to access some file from Chris's computer. Those engineers thought it wise to have some kind of centralized storage with a file-based kind of storage where they could actually pull all the resources they need. So the computer is connected to an existing network and allows users over the network to share the storage space. You just connect, it's more like a storage server computer where you connect it on the existing network and you allow the users to access that storage space.
Hello, Mr. Ssendi.
Yes, please.
Andrew here. Finally, I've sorted out my mic.
Yes, Andrew. Finally.
Yeah, finally. But anyway, this is kind of random.
Yes, please.
Okay. You said, for example, in a network diagram, there are places where you should use IDE or SSD, right?
Yes. No, I said SATA and SSD.
Yeah.
I said IDE is somehow obsolete, and it is very rare to find that kind of disks being supported to date.
Okay.
Because of its low disadvantages. Yes, please.
So, as an engineer, cloud computing engineer or network engineer, there's a point where in your topology, you should maybe use SATA and other place SSD, right?
Yes, please.
Okay, Mr. Ssendi. How does, random question, how does, for example, Google and YouTube work? Because I'm guessing they have storage. What do you think their architecture may possibly be storage-wise?
I think that is something I need to do more research about, so that I give you facts, not what I think. And definitely in the next lecture, it will be our first conversation. But what YouTube has tried to do, at least as per my last research, it leverages more on the caching kind of system. And you will not believe if they tell you that YouTube is one of the lightest or fastest sites available to date. Would you believe?
I do, because I've done my little bit of research on that.
Oh, you have done some bit of research. So most people think that actually YouTube is very heavy simply because it plays videos.
Yes.
But I'll do more research, and then the next class, for the purposes of us proceeding, I will be able to discuss in detail.
Okay, so may I ask a question, Mr. Ssendi?
Yes, please.
What we are studying, is it related to, it is, but is it related to the architecture, for example, of a setup like that?
Is it related? Yes, because you started your question well. You said they have some kind of hardware resources, storage resources somewhere, underlying storage resources, isn't it?
Yes, sir.
So it is important for you and me as aspiring cloud engineers to know at the basic level, what are these resources there? When do I think I use that? And I remember I asked this question: if you want to store data for a long time, what would you use? If you need high speed input, read and write, what kind of storage do you think you should use?
Would it be SATA? Would it be SATA? If I could be wrong, would it be SATA?
If you need, remember they are all using SATA interface. SDDs and HDDs are all using SATA interfaces, isn't it?
Yes, sir.
Unless there are also some other SSDs which use that M.2 SATA 3 interfaces, but still, or NVE by Samsung, but still also they are leveraging on the SATA interface. So, but now we're looking at the HDD, the hard disk, which has platters and spins and disks inside, and they keep rotating, and also looking at the SSD. And we said already in our introduction that SSDs have a high read and write performance, but they have a short lifespan because since it's a chip, the number of times you read and write, you erase, you put data and erase is shorter as compared to that of our original or traditional hard disks.
Yes, sir.
But it also said they are faster as compared to SSDs. Now, these days, what they recommend, more so if you want to have a high performing machine,
can I cut you short? Can I
you
cut you
have
short?
the
Sorry.
operating system running. Yes, please.
Are you saying HDDs are faster than SSDs?
No, I'm saying HDDs do not have fast read and write performance as compared to SSDs. SSDs are way faster. are way faster than HDD.
Okay.
Yes. But in terms of storing data for a
Yes,
very
sir.
long time, and in terms of having huge capacity,
Okay, I've understood now.
yes, HDDs take
Yes, sir.
on the role. For example, if you wanted to have a hard disk of about, let's say 20 terabytes, it would be easy for you to come across a hard disk,
sir.
an HDD, which is not very expensive as compared to you coming across a 5 TB SSD. It would cost you an arm and a leg.
True story, yes.
You're getting the point now. Eh? So if you need to store some huge amount
Yes,
of
sir.
data and high performance of reading and writing performance is not your number one objective, then you need to weigh the alternatives available to you as an engineer.
Okay, may I ask this?
Okay, you seem to have many questions.
I do have like 1 million questions.
Yes, you
Unless
ask
you
that
will answer
last one and we
1,000.
proceed with
But
the
anyway,
lecture. Yes, please.
that last one is SSD drives. What is their lifespan as compared to SATA?
SSD lifespan, I think it's also something I need to find out. But yes, what I've come to appreciate and notice, because if you're using Sentinel, I don't know if you have come across Sentinel.
Oh, yes, sir.
Yes, the life span of an SSD is actually shorter. After you use a disk for some time, and if you keep checking your Sentinel, you'll see your health getting actually low and low as compared to that of an HDD. More so if you don't maybe suppress it to shock, and maybe if you don't maybe put it in maybe abnormal temperatures, you actually have more lifespan for your HDD as compared to that of the SSDs. And experts have done tests. Maybe I'll just need to get time and share those reports with you. But experts have done tests and actually proved that SSDs have a much shorter lifespan or limited write cycles as compared to that of HDDs. I'll look out for those reports and share with you, but I don't have the numbers with me.
I also have a question.
Yes, please.
I had a question, Mr. Ssendi, before you go, sir.
Yes, please. If I suppose
Mr. Ssendi,
so
basically, picture, should we cause?
Okay, so I was saying that NAS typically has its own nodes on a LAN and does not require the intervention of application servers. NAS also allows users to directly access file data over the network, because remember it has already some kind of operating system embedded in it. And this configuration, NAS centrally manages and processes all shared files on the network and releases loads from application or server or enterprise servers, thereby reducing the total cost of ownership and also maximizing customer read over input and output performances. So NAS is a device, just maybe to break it down, NAS is a device that is connected to the network with the file storage function. So just think of it as a storage function device that you connect on the network. And it also delivers centralized file storage and management and separates storage devices from servers, thereby releasing some of the bandwidth, improving performance, and also reducing on the total cost of ownership. So just think of NAS as basically a device rather than a server. Just think of it as a storage device that you attach on a network. Yeah, a NAS is not a compact file server like many people think it is. It is just a storage device. Basically, it is a device that is designed to store files and also to offer file storing functionalities. So the server processes services and storage devices, storage data, while NAS only stores or does the file storing functions. Okay. So
can I ask something?
This is Tisa.
No.
Could I please take the questions during the break?
Okay. Oh, okay.
But you can, if it is burning and you feel like it cannot pass, you can go ahead and ask.
it's okay. I'll ask during the break.
All right then. So we are saying NAS should
Are we having break?
Come again. Okay, NAS should be
Are
able
we
to
having
store.
a break?
You don't want us to have a break?
I was asking because we used to have a break from 6 something to 7.
Yes, we used most of our
Yes.
time discussing questions, but we are going to have a break. We're going to have a break in the next, at 7:10, we're going to have a break. So NAS, we are saying NAS should be able to store and back up large volumes of data and deliver stable and efficient data transfer services. Also, NAS can offer read and write with common interface files and some of the system or file system that we are using in NAS, which we are calling the Common Internet File System. So we are saying that the NAS device can read and write the Common Internet File System or the Network File System And we are saying here, and can also read and write the two systems at the same time. It can even read these systems at the same time. So the Common Internet File System is a public and open file system developed by Microsoft Server Message Block, and the Server Message Block is a file sharing protocol. The SMB, the Server Message Block, is a file sharing protocol set by Microsoft based on the NetBIOS. So users can access data on a remote computer through the Common Internet File System. The Common Internet File System also prevents read and write conflicts and write conflicts to support multi-user access. So if you're looking for a protocol that can help you support multiple user access, we can look at the Common Internet File System. So to enable Windows and Unix computers to share resources and to enable Windows users to use the resources of Unix computers as if they were using Windows NT servers, the best way is to install software that supports these protocols that I've mentioned, the SMB and the Common Internet File System protocol on Unix servers. So when all operating systems support the Common Internet File System, communication between computers are convenient. All right. So I think we can have a break now. We can have a break, and then after the break, we look at reading.
Mr. Ssendi, can we have attendance?
I'm going to share it in a short while, but yes, we're going to have the attendance.
Thank you.
Yes, please.
Okay, so can I ask my question?
Yes, you can go ahead and ask the question, Chiza.
I have two questions. The first one is about the NAS. The NAS is configurable. You can configure an IP address on it, right?
Yes.
Whereas the SAN, you cannot.
You can also configure, because it is a device that you attach on the network and you need to access it. So you can still configure an IP address on it.
So the SAN, where is the IP address configured? Because the one I have seen for NetApp, yeah, one of the companies that does those storage, data center storage devices, the one that I've interfaced with, I just saw like a set of over 24 disks compacted in one enclosure.
Yes.
I don't know whether there was it has a network port or something. So the SAN also has a network port and the like.
Yes, yes, please.
So it's configurable as well as one IP with all its many disks.
Yes, yes.
And then you connect it to what? To the
The
switch?
network, yes, to your network.
You connect it.
Think of it like any device that needs to be connected to the network. But only that this device is offering us storage functionalities. Yes.
So both of them are configurable with an IP address.
Yes, please, because they are network-based applications.
Then how are they connected then now to the servers?
How are they?
Anyway, I think that's where we are going to. Because I'm wondering how they're connected to the servers, because the servers also have their storage in there. They have their disks as well.
Yes.
Because if you look at like the server that is customized and purchased as a server, it has it.
Sorry. So we are saying which we are calling redundant arrays of disk independent disks. Sorry. So we are said that in centralized systems, I've already seen in this picture. I don't know if it was this picture. And we are saying we have some kind of disk enclosures which are controlled, which are uniformly managed by controller enclosures, like some of them SAN, NAS, and our friends have given us very good examples of their experience. So, and we're saying this kind of system supports dynamic storage, capacity expansion, and also improves fault tolerance, and as well as read and write performance. And we were looking at RAID here. We're looking at RAID. And we're saying that they are common RAID levels, but basically they are 7 levels from RAID 0 to RAID, from RAID 0 to RAID 6, 7 levels. So, but there are also common combination of basic RAID levels, such as RAID 1, combining RAID 1 and RAID 0, and also RAID combining RAID 5 and RAID 0. Don't worry, we are going to look at the different RAIDs and what we'll be talking about. So different RAID levels represent different storage performance and data security and costs. So we are going to basically look at the different RAID levels: RAID 0, RAID 1, RAID 5, RAID 6, and so on and so forth. So we are saying here that one of the importance of RAID, it is efficiency, because you can bundle different independent disks together to parallel read and write on multiple disks. And also it is safe because some RAIDs, as you're going to see, have some kind of parity check, thereby being able to recover the data. And also it gives us an ability to do hot backup. Sorry. So let us look at the different or the common types of RAIDs. And we are looking first at RAID 0. This guy here. This RAID 0 is also sometimes referred to. I feel so exhausted. I don't know why. I don't know if there's anyone else who feels like me today, but the week is just starting. But the way
Me too.
You too. Who is that? Andrew? Okay. Someone is telling me to have some rock boom. Energy drinks are not good for you. More so if you are young and you have dreams of making it in life, or if you have made it in life and you're starting to enjoy your money, you'll get problems with energy drinks. There's Kituzi. Hey, okay. Energy drinks, you get diabetes, you get high blood pressure, you burn your calories, your thinking ability. So they're not generally important. But anyway, regardless, you can always exercise and rejuvenate your energy. Okay. Someone is saying Chituzi is not excellent at all. Okay, let me leave the energy drink conversation and we continue with our class. So this is also sometimes called stripping. It combines multiple disks into one key node to node into one logical, all into a logical disk. So this delivers the highest storage performance among all RAID levels. Although RAID 0 delivers the highest speed, it has no redundancy and does not support parallel input and output. So when the data is stored and it is data is segmented based on the number of disks that the RAID 0 volume combines, and data is written into disks in parallel. Therefore, RAID 0 is the fastest among all levels, but we have already said that it has no redundancy. So if you have, this is 500 GB and also this is 500 GB, it will give you a total of 1 TB. Agreed? 1 TB. So if you have this disk 1, disk 2, and disk 3, they are all 500 GB. We shall have our total of 1.5 TBs. So they are telling us this gives us the highest storage performance, but it has no redundancy. And let's look and try to understand why it has no redundancy. As you can already see here, we have our different data or our different data parts which are stored differently on our data. So what happens with this is that the data that is going to store, just think of this as our different data parts. So if this is our song or our file which we need to store, which is broken down into different data types. One different data types, remember everything goes back and is written into binary in our computer. So just think of it as different bytes of data are stored on different machine. As we're having our data part 0 stored here, our data part 1 will be stored here, 2 there, 3 here, 4 there, and 5 there on different files. Let me ask a simple question. What will happen if this disk fails? Will you still be able to access your file here, or it will be corrupted?
You will still be able to access.
Are you sure you'll still be able to access the file?
No.
Okay, true. You won't be able to access your files because already we have seen it has the highest storage performance, but at the same time it has no redundancy. So if one disk fails in your array, then it means your entire data set is corrupted.
Good.
It's gone. Exactly. So theoretically, the total disk performance here equals to the performance of a single disk multiplied by the performance of the disk. So if your disks can read up to, let's say, 7,200 RMP, or maybe, okay, let me just say if they can read at 6 Gbps. So the speed would be 6 times. We have 2 disks. So our total read and write performance will be 12, theoretically, 12 Gbps per second. And that is what we are calling RAID 0. We already seen that RAID 0 delivers high speed read and write performance, but it has no data redundancy, and I'm repeating that so that it sticks in your heads. So it is applicable to applications that have fault tolerance for data access and applications that can regenerate data through other methods, such as web applications and media streaming. Let us also look at RAID 1. RAID 1 here. It's what we want to look at. So RAID 1 sometimes is also referred to as mirroring. You know what a mirror does? It's also referred to as a mirroring, and for it, it is basically designed to maximize the availability and repairability of user data. RAID 1 automatically copies all the data written to one disk to the other disk. If we have our song here, your favorite song here, what will happen? It will save the entire song file on this disk 1, and it will copy the exact data parts to the other disks, or to all other disks that are available in your RAID. It will make a copy of that file to all the other disks available in your RAID. So RAID 1 writes the same data to the mirror disk while storing the data on the source disk. So when the source disk fails, the mirroring disk takes over services from the source disk. RAID 1 delivers the basic data security. It delivers the basic data security. My handwriting, but let me just write security. It delivers the basic data security among all RAID levels because the mirror disk is used for data backup. But the advantage or the disadvantage we are seeing here, regardless of how many disks we are having, the total capacity of your RAID will always be equal to the capacity of the smallest disk in your RAID. If let's say all these disks are 500 GBs, could someone tell us how much capacity do you think our RAID will have if we have disk 1, 2, 3? Okay, let me just use 4 disks and 4. If we had 4 disks, how much do you think our total capacity would be?
500 GBs.
500 GBs, yes. So you already seen that there's some kind of disadvantage. It does not utilize so much on the storage performance, though it gives us security for user data. But in scenarios, there's no way sometimes you're going to explain to your IT manager or to your manager, depending on your level of supervision, that you know what, we bought 10 500 hard disks with 500 GBs, sorry, 10 500 GBs hard disks, but the total capacity we are having on our storage is 500 GBs. If you are the manager, would you understand?
Not at all.
Not at all.
No.
What would you
No.
tell your system administrator? Eh? Okay, so we are saying that RAID 1 is the most expensive storage unit among all RAID levels, and it delivers the highest data security and availability. Basically, it is applicable to online transactions, applications with intense read and write operations, and other applications that require high read and write performance and reliability. For example, email, operating system, application file, and random access environment. That is RAID 1. Let us look at also RAID 5. I'm trying to draw my cap thing here. Let us also look at RAID 5. We are saying that here RAID 5 is the most common RAID level in advanced RAID systems, and it is widely used for its superior performance. Are we together? And data redundancy balance design for its superior performance and data redundancy. And we're going to look at it and actually come to understand why. It is short for independent data disks with distributed parity. RAID 5 uses parity. I'm sure you're already seeing the P's here. Yes? Remember, maybe I forgot to mention, when you are RAIDing, we are coming up with different disks, independent disks, and we are RAIDing them to come up with one logical disk. We bundle or put together our independent disk, and we want to come up with our logical disk. The same also applies here, and we are coming up with our logical disk. This is our logical disk that is coming from our RAID here. Okay, so what this one does, it is also sometimes referred to as are independent disks with distributed parity. RAID 5 uses parity for parity check and error correction. As you can see in this diagram, there are there's some disks which we are using, and you see this P is the check value of data and the D is the actual data. So RAID 5 does not back up the stored data, but what it does, it stores the corresponding parity data. It stores the corresponding parity data on different member disks. I don't know if you're seeing these different member disks. So when the data on one member disk here, disk 1 is corrupted, the corrupted data can be recovered based on the data or on other member disks. And we are saying that's why RAID 5 is a storage solution that balances both storage performance, data security, and storage costs, because we have redundancy. So if one disk fails, we can actually recover our data based on the different parity checks, and they help us to recover our data. For these guys are using, I don't know if some of you have heard of equations. So they are assuming that if we have our 3 variables, yes, and we know that 1, or let's say they know that 2 plus 2 is equal to 4, isn't it? So if 2 here is gone and we have 2 plus x is equal to 4, even if you don't know this 2 here and it has disappeared, won't you be able to recover and you know this was 2? Some people who did some maths here.
Yes, you
It
can.
should be possible.
It should be possible, isn't it?
Yes. Very.
Even if,
Yes.
let's say we didn't know the answer, our third parity check here is spoiled, and we have our 2 plus 2, we already know our answer, isn't it? So for them, they do not necessarily back up data, but they are using different corresponding parity check on the different member disk to recover that data. And we are saying this kind of solution is the most commonly used because it is a solution that balances storage performance, data security, and storage costs, because it gives us a redundancy of 1 disk. And also the minimum amount of disk you can have in this RAID are 3 disks. Take note of that. Okay, so let us also look at RAID 6.
Pardon?
Yes, please.
Pardon, a bit behind there. I didn't get the last point. The last point you said.
Oh, I'm saying the minimum disks you can have to implement this RAID 5, they should be 3 disks. Are we together? Okay, so let us now look at RAID 6. Let us look at RAID 6. We are saying
I
that.
have a question.
Can you ask it after we are done looking at RAID 6?
Okay.
Then you can ask it. I'm going to come back to you. Thank you. So let us look at RAID 6. RAID 6 is RAID mode is designed to further enhance data protection. So compared with RAID 5, RAID 6 has an independent parity block. It has an independent parity block. In this way, each data block has 2 parity blocks. One is a hierarchical check and the other is the overall check. Therefore, RAID 6 delivers high superior data redundancy performance But two parity check mechanisms slow down data read and writes, because whenever this data is created, it has to create one parity check, then it also creates another independent parity check for it. So we are saying this also in a way slows down the data write performance. So the RAID controller design is more complicated, and two parity areas reduce the available space, because also these guys have to be stored on the segments of the hard disk, like you can see in this diagram, which is illustrated there. So common 6 RAID technologies include that PQ and DP. The two technologies use different methods of obtaining verification information, but both technologies allow data loss on two disk arrays of two disks in array. So what this guy does, since it has two parity checks, we can afford losing two disks. We can afford losing two disks in an array, and we still have our data still running, up and running. Okay. So data security of RAID 6 is higher than that when you're looking at security, because we can afford losing two disks here already. Here we can lose one disk. We are already saying that data security of RAID 6 is higher than that of RAID 5. Even if two disks in an array fail, the array can still work and recover the data on the faulty disks. But this design of the controller is more complicated, and we already said that the read speed is lower and it takes a longer time to calculate the parity checks or the check information, and also to verify the data corrections. So when write operations are performed on each data block, two independent check calculations need to be performed. We're already seeing that this is resulting into system overload. So the disk usage is lower, and also the configuration is more complicated. So RAID 6 is applicable to the environments that really require high data accuracy and integrity. And that summarizes our RAID combination for us, our different levels. Yes, Teresa, you had a question?
My question is on number one, are these RAID levels compatible? Like, can you choose one and then mix it up with another one on the same network? The number two, second question is on RAID 5. I'm sort of wondering, where are we coming from? We are coming from logical to separated disks, or separated disks to logical. When you say in RAID 5, we can lose one entire disk one, where is the replication of the data to to recover it? Where would the data move to? Yeah, those are my two questions.
All right. Thank you, Teresa. I see Johnny Tony Blair, your hand is up.
Yes, please. Thank you so much, Mr. Ssendi. I think this is the first time of you hear my voice, but yeah, thank you so much for the opportunity. And my question is on RAID 1. You talked about, if disk 1 gets an issue, then information is copied, is already copied on disk 2. So my question would be like, can it bring anything like duplicates in someone's information or something? Yeah, thank you.
Okay, thank you. Thank you so much for that. Let me first answer Godwin before I go to Teresa's question. RAID 1, like it is the word mirroring. You only access the source disk, and in case of failure, that is when you access the other disk. That's when it comes in and plays the role. Then you, the network engineer or the system engineer, you get another disk, because it also allows you to hot swap, put it in, and then this disk also will mirror. It just mirrors for data security or for backup. It just mirrors the entire disk, and only the active disk is accessed when in terms of read and write. Only one disk. So all these other disks that are in this RAID are actually disks to be mirrored at. That's why they are called mirror disks. There are disks to be mirrored. Actually, in actual sense, think of it as disks for backing up data. I don't want to use the word backing up data, but they are just disks for mirroring this other disk. So in case one of these disks fails, then the other disk will get and also mirror the other disks. But you are only actively accessing this disk. So what is on this disk is what is on this disk is what is on that disk, and is also what is on other disks. It is just mirroring. Okay, but like we said, it has the least storage performance because it will give you the total capacity of this RAID enclosure. It will give you the capacity of one disk because the rest are just mirrored, and think of it like for backup. And now, Treasure, just to explain briefly, we're not coming from logical to different disks. We said in centralized environments that we can have one kind of centralized storage device, yes, or what we are calling a disk enclosure, which is having many disks together, put together, which when we RAID now, these disks inside this enclosure, we can come up with our logical disks. So in actual sense, we are RAIDing these hard independent, redundant independent disks to give us one kind of large, I would say, logical disk. You have like 2 TB, 2 TB, 2 TB, so you bundle them together or you bind them together to form one logical disk. So we're not coming from logical disks to separate disks. So think of this enclosure as having these disks now. But as we are RAIDing, what types of RAIDs do we have? And these are what we're looking at today. And we looked at RAID 0, we looked at RAID 1, the most common ones. We looked at RAID 5, and we also looked at RAID 6.
0156.
Is that okay, Teresa? Are you with me?
Yes.
Yes. So, and we are saying this device here,
yes,
this example that you're seeing, it has different, maybe someone could have raided, could have put their RAID level at RAID 5. Are you getting me? They could have raided it at RAID 2. Or RAID 1 or RAID 0, but we are saying the most common RAID 0, RAID 1, RAID 5, and RAID 6.
5 and 6.
And they are the ones we are looking at today. So this storage device here is actually having different independent disks inside it, which we are now putting together to come up with our logical disk, which our now servers will access and read and write data. And we said in our RAID 0, what will happen is this gives us the highest storage performance because the total speed or even the total performance or capacity of this RAID will be the total number of disks inside this RAID 0. If you used RAID 0 in the previous diagram, I would show you, and you have one, this is 500, 500, and 500. How many total capacity would we have?
1.5.
1.5. And that happens how? Because now as you're writing data on these disks, you remember data is broken down into bytes, isn't it, to binary, isn't it? So as you're writing down your data, different bytes or data segments or data blocks are going to be written to different disks. And they are written to them sequentially. That this one is going to be on this disk, data 1 on this disk, data 2 on that one, data 3 on disk 2, data 4 on disk 1, and data 5 on disk 2. So which disadvantage do we have if all of our disks are having data on them? If one disk dies with its data, you realize now this segment of this file is lost. You realize this segment of this file is lost, and you realize this segment of this file is lost, and we have a corrupted file. Unless if there are other backup mechanism, ideally RAID 0 does not give us data redundancy, or it does not lead to reliability. Trace, are we together? And we are saying for you to be able to implement RAID 0, you need at least 2 disks to implement RAID 0. And the same is also applying to RAID 1. We need at least 2 disks. Yes. And I'm saying at least 2 disks to implement this. But now when it comes to RAID 1, which we're also calling mirroring, what will happen is that disk 1 will just mirror itself to disk 2. But whenever a user is accessing and reading and writing data on them, he will only access one disk at a time, the source disk or the active disk. He will read and write data from the access disk. But in case now this disk becomes faulty, what the system administrator will do, there will not be data loss. There will not be data lost. He will just hot swap out this disk which is faulty, put in another one, and this data again is mirrored on another disk, and the user is able. What happens if this one becomes faulty? The user now is able to access and read data from this other device. So when he puts in another drive, so this drive also, because it is RAID 1 or it is mirroring, it will mirror all the data on it onto another disk, or even other disks if they are available and you configured your RAID level to be RAID 1. And also we look at RAID 5. With RAID 5, we are saying you need at least 3 disks inside the enclosure which I showed you here. This enclosure here. Where is it? Not distributed. Yes, inside this enclosure, if you're going to do RAID 5, you will need at least 3 disks inside, 1, 2, 3, for you to be able to perform RAID 5. Or you can have more, but the moment you configure it as RAID 3, what will happen is it's going to use parity checks to either restore data or repair it. So it will add a parity check on top of the data that is stored. And if one disk is lost, RAID 5 also gives you an ability of you can actually lose one disk and you still have your data. So the moment you put in the other disk, it will use this parity check to be able to restore your data on this disk, and you're good to go. And also looking at RAID 6 here. With RAID 6, we are saying you need a maximum of 4 disks. Maybe before I talk about RAID 6, I said here that this is the most commonly used because of its ability to try and balance storage performance, but also at the same time to balance data security or its redundancy. At least it gives you a redundancy of 1 disk. Now for this one, you need at least 4 disks for you to be able to configure and set up your RAID to level to RAID 6. And it gives you a redundancy of about 2 disks, that even if 2 disks fail, you are able to plug in your other 2 disks, and then you use this parity check and the independence parity check to be able to restore data or even repair data on those disks. But since the process takes longer, it is slower than RAID 5, and that's why now we said RAID 5 is the most commonly used because of its ability to try and balance both data redundancy and storage performance. Okay, Teresa, I hope I've answered you. Friday, I see your hand is up.
Okay, thanks for that on the issue of RAID. My question is on RAID 5.
Oh, sorry, before you continue, Friday, Teresa asked also, can we combine different types of levels. We said there are also some kinds of levels actually which are combined and used together. And we talked about some of those common ones. We said like 5.0, we said 1.0. So those are some of the different levels that you can put together and you combine them and you're able to use them concurrently. Yes, you can go ahead and speak. Yes, Friday. Sorry to cut you short.
My question is on RAID 5.
Yes, please.
We talked about that when you lose one disk in that RAID, you can recover from the other. But my question is, what happens when I lose two disks in that RAID? Does it mean that I will not recover the other data?
Yes, when you lose two disks and you are using RAID 5, you see the answer is obvious. You will not be able, because RAID 5 gives you at least a redundancy of one disk. But if you're using RAID 6 and you lose two disks, then you are good to go. But you see, under normal circumstances, it is very rare and hard for you to lose more than two disks or even one disk at the same time. Unless when there's something that is out of the ordinary. And sometimes if that something is out of the ordinary, then you could actually end up losing the entire enclosure.
Mr. Ssendi, can I share something?
Yes, you can go ahead and share, Shamil.
I don't know if you can allow me to share my screen and I demonstrate something.
True. You can share. You can go ahead and share. No worries. Are you allowed, or like try and share? Let me first stop sharing mine. You can try and share. All right.
Are you able to see?
Yes, we are.
Okay. I just want to show a scenario about RAID. This is a NAS system. And like the way you're saying, you're talking about 3 disks. I want to show them how RAID 5, for instance, works.
All right.
These are 4 disks, and each disk is 10 terabytes. They're into an enclosure, which is a NAS. So you find that in most cases, RAID is used to form the logical storage, like the way you've said. For instance, when you look at your RAID 0, the main purpose is like to pull different disks into one pool, and there is no any security. So when you look at RAID 5, for instance, we're looking at 5 disks, but when you configure them with RAID 5, it's going to give you total usable space of 3 disks. These are 4 disks, but we shall only have total usable space of 3 disks because one disk is killed for the parity checks, so that anytime someone wants to change a disk, they are able to swap it without any interruption to the data. So maybe another thing which my colleagues should know is that with the RAID system, most cases, the hardware comes configured with the options. Like you can see this RAID 5. So it's a matter of picking which RAID you want to use. So it depends, what do you want to achieve? So the main purpose is you have to understand how RAID works. The configuration is almost seamless. Now with the combined RAID, like if you want to use RAID 5.1, in most cases, you find the hardware comes with the RAID 5, then for you have to have a software which will do the 1. So in other words, you want to do both parity and mirroring. I don't know if I'm making better sense.
Yes.
So what this means, like for instance, practically, my storage pool is now coming to 30 terabyte instead of being 40 terabyte, because we are seeing we have 4 disks, but when you come to the pool, it will only give me 30. Because one disk is killed for those parity checks because it's running on RAID 5. So you'll find that another person will ask, how do you pull that storage now into use after you've done the RAID? So like previously, you've been talking about the high SCSI. This is the SCSI manager.
Yes.
So it will give me the protocol which I will use to communicate with the servers. So I'll create targets. So each of these targets can be presented on a server. Like for instance, now if you look at this server, you find that it's connecting to those targets and you're getting, I talked about SCSI initiator. So these targets are direct from the NAS, but when you connect them onto the server, they'll present like
hard disks.
hard disks attached to the server. Yet this server, its hard disk actually, it's only this and these partitions. But these three are direct from the other pool of storage. And if I try to disconnect one of the targets from here, let me say if I want to do this backup, if I disconnect it from here, it will also disappear from there. If I disconnect, oh, sorry, it's being in use. I wanted to just mirror that. But when you disconnect that target, it also disappear from here. So I just want members to have that feel that when you create a pool, how do you present it to the servers? Doesn't mean that once you've created it from the other side of the storage, it's automatically on the servers. Also in the people using Linux and all that, they present them differently. Thank you. That's what I wanted. I don't know if now it throws more light because I've seen there are so many questions about RAID.
All right. Thank you so much. It indeed throws a lot of light, and I think some of them have been able to see you being able to use what we have been actually talking about in reality, so it doesn't sound more like alien science. So team, yeah, I'm seeing Kugonza Stephen is saying good job, Shami. Jane is saluting you for the illustration. Thank you so much, Kwesiga, for that illustration. It has been very helpful, at least to me, and I believe also to some of us in this forum. And this brings us.
Sam,
yes, please.
Let me just voice it out to Shamil. Shamil just took all the risk of sharing, of sharing the live network with us. I mean, that's
True.
a big risk, and we just thank you. It's a big risk, though.
Yeah, I know it's a big risk, but whatever IP someone has looked on, they are private, so they are not routed.
but anyway, thanks. You're the best.
I know most people hide things because of security, but I'm sure of the security I have behind. I have so checks in terms of security, yeah.
All right.
But I just wanted someone to have a touch, because you see most of these things theoretical, even at university, when we are studying, you don't put the visual impression. But there are things which work. Like, for instance, I talked about a mobile drive. These are things which are really so much into use. But you find someone who will be like, no, home drive. But you find everyone at saying, please save your work on a home drive so that you avoid data loss and all that. But people never take it serious. The day you have such a scenario, that's when you'll be like, oh God, I wish I'd done that. So some of those things, when we look at them, we take them more serious. So RAID, the truth is RAID 5 is high in use, actually compared even to RAID 6, though RAID 6 gives us more better parity checks and corrections in terms of recovery. But RAID 6, like the way you have said, it needs, you kill more disks, though it will give you that chance of having more than 2 disks for you to exchange in terms they are faulty, but in actual environment, actually, disks rarely fail.
True.
And the way those systems are made, like the NAS and the SAN, when you look at their managers, you always get reports. So if you've configured like to get an email and so on, you can tell that the disk is about to fail. Actually, that system, like I've shared, it has even what we call a hot spare. You can always load a disk and you call it a hot spare. In case one disk is starting to fail, automatically it goes into the production. So that gives you more lead time to procure even another disk and to be on standby. But to my experience, actually, even in Google, when their disks are failing, the rate at which they fail, it's really very low. Yet for them, they're handling almost data traffic for the entire world. So for an enterprise like a bank, you can find even in a year only one disk has failed. So it gives you better time. That's why people rarely actually use RAID 6, because it kills more disks. When I say killing, it means if you configure 4 disks, for instance, already 2 disks are not usable. You only have storage for 2 disks. So because of that, people find it like RAID 5 is already giving you the security.
True. All right, team. I think today's discussion has been good. Thank you so much, guys. This is it for tonight. I don't want to overshoot. It's already past 8, 15 minutes past 8. So allow me to wish you all a good night. Thank you, Kwesiga, once again. Thank you, everyone, for sharing. Thank you, Triza, for participating, each and every one of you. It is something I appreciate and I don't take for granted. Jean, thank you. Thank you, Enoch. And let me wish you the very best for the rest of the night. Enjoy your night. Don't forget to go and try out those quizzes. Try them out one more time, as many times as you can. And yeah, I wish you the very best. You know that. So good night to you all.
Thank
See you
you,
tomorrow.
team,
I want
and
to
good night,
mention that
everyone.
tomorrow's class, I'm suggesting that we start at exactly 6 p.m. It is my humble request, and I pray that you will honor it.
I think it's okay.
All right. Thank you so much. So tomorrow, I'll be sharing the links in the morning, but we shall be starting at 6 p.m. Thank you so much for honoring my request, and have a good night to you all.
Hello, excuse me, teacher.
Yes, Tito.
Mr. Ssendi, good evening, sir.
Good evening to you.
Well, thank you for everything. We appreciate.